Hello, my name is Stefan Bruns and I'm with Fraunhofer IST in Germany. Today I will give a talk about the coating of UV bandpass filters that are based on tantalum pentoxide and zirconium oxide for solar observation. At first I will give a system overview to see where the filters will be used in the final arrangement. Then I come to an experimental part where I give some details of the design concepts and also the coating equipment. And finally, I will show some results of the deposited filters. The motivation. The Max Planck Institute for Solar System Research is working on a project that is called Sunrise 3. They work on a balloon-bound solar observatory for the investigation of magnetic field and plasma flows in the solar atmosphere. Their system wants the spectropolarimetrically sampling of the solar spectrum from near UV to near IR. The UV region is hardly accessible from the ground because of the atmosphere. Right in this region there are thousands of spectral lines from different materials. The so-called SUSI system can extract several hundreds of these lines in the wavelengths range from 309 to 470 nanometers with its high-resolution cameras. The filters are used as order sorting filters at this position, and also you can see it here, and they are tilted by 2 degrees. This makes it essential that the bandpass and the blocker are on one side to have no backside reflections and to reduce the ghosts. Experimental part. The filters were deposited on the EOSS Sputter coating system which was developed in our institute. The process is based on mid-frequency sputtering of thin metallic layers to a rotating turntable. A RF plasma source oxidizes the thin metallic layers. It is called the meter mode process. We use it for silicon cylindrical targets. In the case of high refractive index materials, tantalum pentoxide and zirconium oxide, we use the CAST process, compound-assisted reactive sputtering. In this case, the targets contain some amount of oxygen also. It is important that we do not use any additional oxygen in the sputtering compartment. This makes the process very stable. The whole machine is fully optimized through the production control MOCA+. It is in broadband monitoring system, but also controls the whole machine. The enhanced optical sputtering system EOSS offers extremely stable processes. It can be used without complex process control because of the separated process chambers with metallic deposition. The cylindrical targets offer a large amount of material. The deposition rate nearly does not change because there are no racetrack trenches. Thus, the system combines the stability of IBS processes with the throughput of evaporation. The EOSS concept was transferred to industry where it could be used over more than 4 weeks without cleaning, even in production environment. Together with the monitoring system MOCA, it is designed for fast adaptation to meet customer demands with high optical quality. For this project, we used a new design of high-purity zirconium targets. Special focus was on low iron oxide and titanium oxide concentrations. The cylindrical targets are plasma sprayed and contain zirconium oxide, but the conductivity makes mid-frequency sputtering and CAST process possible. For comparison, you see absorption results from different targets on the right. Actually, these are the total losses that are calculated from the transmittance of 2 micron thick layers. The black curve is from a metallic target from standard material ZR702 in pure meter mode. Even the addition of quite a lot of silicon did not help to get as low losses as needed for 80% transmittance at around 300 nanometers. Another spray target without focus on low impurities had even worse values as can be seen in the red line. The high purity target, together with the addition of only a few % silicon by co-sputtering, suppresses the crystallization and reduces stray light losses of the layers. This gives the low total losses of the green line, which is the process we used. With a similar deposition rate, but no silicon addition, there is a huge effect from crystallinity, which was determined by X-ray diffraction and can be seen in the blue curve. The refractive index was initially determined using elapsometry from single layers and is around 2.1 at 550 nanometers. The dispersion was fine-tuned from the final transmittance measurements of each layer from a complete layer stack using OptiRay. The substrates from UV fused silica had a size of 40 × 40 × 8 mm, and the coating should leave an open aperture of 38 mm. For this reason, the substrates were lying only on the edges during the deposition in sputter-up configuration. Besides P4 polishing, the surface figure requirement was below 65 nanometers. The optical design of the layer stacks was made using OptiLayer. At first, a bandpass based on 3 cavities in a quarter-wave thickness design was calculated. Then, the blocker was designed by gradual evolution with an anti-reflection range around the bandpass wavelengths. Finally, the stacks were put together with most of the layers fixed. Only 4 layers at the connection were used for adjustment. This leads to quite thick coatings with more than 20 micrometer and layer numbers from 216 to 252. For the backside, an anti-reflection coating with less than 0.2% residual reflection was calculated. A stress compensation layer was added. I will come back to this later. The deposition was controlled using the modular optical coating control application MOCA that was built in our institute. We decided to use 4 to 5 monitoring substrates depending on the layer number. Within this, the first monitoring substrate is used for the quarter-wave thickness bandpass and the first layers of the blocker. On the next slides, I want to show some details of our in-house developed MOCA system. You see light that comes from the position machine to a reflective collimator that puts the light into the fiber. MOCA is not only designed for the optical monitoring, but also for the control of the whole deposition machine. We have the coating steps defined in material recipes inside the database. In this part is also the batch definition located with details on machine preparation and the stack of single layers. The process control is able to do fully automated production, including substrate handling with pre-planned batches. It can do a stack re-optimization connected with OptiRay or OptiLayer. It is also able to learn the deposition rate from optical monitored layers for further time-controlled layers. This can be used for coatings where no monitoring substrate exchange is possible. You can also do some pre-calculation inside the software to define the monitoring routine. A virtual deposition run is available to detect difficult layers and to get an opinion of the outcome. The optical part of MOCA is made from high-quality equipment. The spectrometer system is based on size components for UV to near-infrared range with long-term stability. The light comes from a stable halogen lamp, and the pass is designed robust with reflective collimators and fibers. Measurements are available for every turntable rotation. In our case, at 250 rounds per minute, this means every 240 milliseconds. All 3 parts of the transmittance measurement, reference, dark, and sample, are made each rotation. The typical integration time is 2 to 3 milliseconds. This means you get your thickness evolution in very small steps. On this slide, you can see on the left a sketch of light path beginning from the halogen lamp via fiber to the reflective collimator. Then, as an open light beam through a tilted window, into the deposition machine. In the rotating turntable is an opening for the reference. You can see this in detail on the right. The further way is similar, but the light is splitted into 2 spectrometers by a fiber with 2 arms. Next, I show some results of the filter coatings. We started with a coating of bandpass filters at 399 and 355 nanometer, which could be performed with tantalum. First test of a bandpass with 20 layers is shown on the right as red curve compared to the initial design in black. The mismatch from design is only a shift of well below 1 nanometer, but a nice shape. Also for the process with zirconia that was used for 316 and 327 nanometer, a nearly perfect match could be realized using the broadband monitoring. The wavelength range for the transmittance measurement was only from 380 to 1650 nanometers, and thus we used only an extrapolated dispersion without a huge effect on the bandpass. The shape of the bandpass stayed in good match even for the complete coating with more than 200 layers which is shown in this graph. It also includes a backside anti-reflective coating with 2 micron stress compensation by silicon oxide layer. For the 360 nanometer coating, blue curve, the absorption was slightly underestimated during the design in black curve. Annealing of the filters brought the transmittance in red line over the threshold of 80%. For the 327 nanometer filter, no annealing was used. As an example of the thickness errors from the single layers, I show this graph with results from the Mocha monitoring. Here we see the bandpass at 399 nanometers with 4 monitoring substrates. The exchange layers are plotted as blue lines. The thickness deviations are on a very low level throughout the complete coating. Only slight increase can be seen at the end of the last monitoring substrate that controlled 80 layers. The calculated deposition rate remains very constant. At the beginning, the machine was brought to the temperature region where it saturates during the process. Thus, you do not see any changes at the batch start. Also, the exchange of the substrates without additional heating phase does not lead to another detected deposition rate. The broad blocking range of the filters in terms of optical density is plotted in the graph on this slide. It is defined from 200 nanometers to 1100 nanometer. We see one of the tantalum in black and one of the zirconia filters in red. The overall optical density should be better than OD3 and reaching OD5 next to the bandpass area and at several wavelength ranges of higher order lines. Because of the slightly lower refractive index contrast and smaller full width half maximum, the bandpass at 360 nanometer needed some more layers than that at 399 nanometer, although the density is lower in the visible range. We needed some stress compensation to meet the surface figure requirements. This was done as a silicon oxide layer below the anti-reflective coating on the backside. We measured the profile of 2 fused silica substrates with a thickness of only 1 mm at a DECTAC system over a range of 40 micron. You can see some measurements of one example in the graph on the right side. From the maximum height value, we calculated the stress for all coatings using the Stoney formula. It was in the range from 50 to 80 megapascal for the zirconia-based filters and in the range of 90 to 110 megapascal for the tantalum-based ones. We decided to not fully compensate the stress to minimize the losses and apply 2 micron silicon oxide for zirconia filters and 5 micron for tantalum filters. With this, I come to the conclusion of my talk. We demonstrated the capabilities of zirconica cylindrical sputtering targets. They are a cheaper alternative to hafnium sputtering targets for the UV spectral range. We could show very good optical properties, down to 300 nanometer wavelengths. Also, we could show the potential of the Mocha broadband monitoring system. The transmittance of the coating and of the design were in very good match, despite the bandpass wavelengths was out of the range of the system itself. We could send the parts in 3D printed boxes to our partners at the Max Planck Institute in Göttingen, and they have made a thermal vacuum test with the parts installed in the holder. They have successfully passed this test, and now they are in the integration and verification phase in the SUSI system. Thank you for your attention. I would appreciate your questions in the following discussion, but I would also like if you contact me later via email or telephone. The work was partially funded by the German Federal Ministry of Education and Research as well as the Max Planck Institute for Solar System Research.